Hi everybody. So we have a new audience. They are religiously practicing social distancing. So hopefully we'll be able to end all of this soon. Okay, we are starting a new unit. It's exponents. We're going to start by talking about the properties of exponents. So you probably know a lot of these properties, but I'm going to go through and list them all, and we'll prove a few of them. So the first one is a to the x times a to the y is equal to a to the x plus y. So the base has to be the same, and if we're multiplying, then we can add the exponents. Now we can say the same thing for division. I'm numbering these, but again, it's just so that it's a little bit easier for us to refer to later on. It's not that there's any order to these. So if we're dividing and we have the same base, then not surprisingly, we can subtract the exponents. And then exponents, we already talked about the fact that they can distribute into parentheses, but they can only distribute into parentheses if inside the parentheses we're multiplying. So this is a times b, so we can distribute the exponent and it becomes a to the x times b to the x. And again, this holds true if we're dividing. So if we have a divided by b, and we're raising that to the x power, then we could say that this is a to the x power over b to the x power. Then we also have anything to the 0 power is 1. If something is being raised to a negative power, then we can make that power positive by putting the a to the x in the denominator. If you raise a power to a power, so if you have a to the x and you're raising that to the y, then you multiply the powers. And that's what we're going to do for now. There are a couple of more with radicals, but we'll take care of that later. Okay, so let's take just some of these rules and prove them. We're not going to go through every one, but I want you to just get an idea as to why things distribute, why we, in this rule number 1, we can actually add the exponents, so that you're understanding why these rules exist and that they're not just coming out of nowhere, kind of like that quadratic formula that we proved. Okay, so let's take the first one. Let's prove this first rule, that a to the x times a to the y is equal to a to the x plus y. So what we're going to do to prove this is we're just going to expand everything, okay? So by definition, a to the x is equal to a times and I'm going to put a dot, dot, dot here. We don't know how many a's there are because this is being raised to the x power. So what we're going to do is we're going to put a dot, dot, dot. That just indicates that there are more a's in between. And we're just going to say that this is occurring x times. And then we can do the same thing for a to the y. So a to the y is a times a, and the same thing. We don't know how many a's there are. So we're just going to say y times here. Okay. So now that we've expanded each of these, we're going to multiply them. And the idea here is that we're going to make the left side equal the right side. Okay, so we're starting on the left, and then we'll move on to the right. So a to the x times a to the y is just what we have here times what we have here. So we have our a times a. Again, we're not sure how many there are, so we're just going to say that this is happening x times. And then we're multiplying by a times a. Again, we don't know how many there are, so we just multiply it. We just put that dot, dot, dot in there. And this is y times. Okay. So each of these, we could put a reason. So for each of these, we're going to put definition of exponents. Because this is what exponents is. It's just this repeated multiplication here. Okay, and that's true for both of these. And then over here, we're actually multiplying. And when we multiply x times, and then we multiply y times, then when we put it together, we have x plus y. So we have xa's, we have y's, so now we have x plus y of them. Okay, now what we're going to do is, so this is our left side. Let's put that in this nice blue here. This is the left side. Okay, now we're going to do the right side. And if we had a lot of room on this paper, then we might actually put this stuff on the left and then what we're about to do on the right, but we don't have that much room. So we have a to the x plus y now. So a to the x plus y, by definition of exponents, is a times a. And again, we don't know how many a's there are, so we're going to put a dot, dot, dot. And this time, all we know is that this is x plus y times. And once again, this is just because that's what the definition of exponents is. So notice we're putting reasons in here, just so that when people look at our work, they can follow along and know where we're getting this information from. And this is the right side. So now what we have is the left side is equal to the right side. A to the x times a to the y is equal to the a to the x plus y. They're equal to the same thing, okay? If they're both equal to the same thing, then they're equal. So we can make that conclusion. So what we do is we use something called a therefore. So these three dots mean therefore. And we do this at the end of every proof. What we're doing is we're saying, see, we're going to put in this last statement and say, okay, our last statement is our proof. It's saying that the left side is equal to the right side. Again, this is just to be clear. So a to the x times a to the y is equal to a to the x plus y. And our reason here is that they are both equal to the same thing. Therefore, they're equal to each other. Okay, this actually has a name. It's called the transitive property. So you don't always have to write out this whole thing. You would just say transitive property. Okay. And when we're done with a proof, what we can do is we write something called QED. So this is a Latin. I don't even remember what it stands for. But you'll see this at the end of every math proof. And essentially what it means is, we did it, we're done. So in Latin, that's what it is. It's saying, we did it, we finished. And it's another way to indicate to people that, okay, this is the end of your proof. So you have your therefore statement here. Therefore, a to the x times a to the y equals a to the x plus y. But then this is like your celebratory message. Okay, let's do another one. Let's do the distribution one. So another proof, this time we're going to do AB to the x is equal to a to the x b to the x. Okay. So this is our distributive property for exponents. And we're going to do the same thing. Okay, we're going to make the left side equal to the right side. So we're going to start with AB to the x. So AB to the x is AB times AB. And we just keep going. Again, we really don't know how many ABs there are. So we're just going to say that this happens x times. And our reason here is the same as before. It's just definition of exponents. So now we can actually rearrange this. So we can use, this is all multiplication. This is a times b times a times b times a times b, and so forth. So we can rearrange this and we can say ab to the x is really a times a and so forth times a, and then times b times b times b. There are x of these, and there are x of these. All we did is rearrange it. bringing all the A's to the front and moving all the B's to the back. And we're allowed to do that because multiplication is commutative. Okay, commutative property says the order doesn't matter. So A times B is equal to B times A. Okay, so AB times AB is the same thing as AA, BB. There's no difference. We can change our order around however we want. Okay. Okay, so we did the left side. So we can mark that off. This I usually wouldn't put in a proof. Again, it's just because we don't have a lot of room, so I can't put the left side on the left and the right side on the right. So we're just indicating the difference. Now we can expand the right side. So the right side says a to the x times b to the x. And we know, using the definition of exponents, that this is a times a times a, x times. And then times b times b times b, also x times. Okay. And that's just definition of exponents. So now the left side is the same as the right side. We showed that they're exactly the same. So this part here is the right side. So now we can go back to our therefore statement. Therefore, a b to the x is equal to a to the x times b to the x. And this is the transitive property. They're both equal to the same thing, therefore they're equal. Okay, transitive property is essentially saying C equals D and K equals D. So C is equal to K, if that makes it easier for somebody to see. Okay, it's just that two things are equal to the same thing, therefore they're equal. And then because we're done with our proof, we can just write QED. Let's do one more, just so that you have an extra one in there. Let's do a proof of that seventh rule. So this is a to the x to the y is equal to a to the x y. Notice that these proofs aren't particularly long, okay? All they are is just using the definition of exponents. So a to the x is equal to a times a. I'm going to put in the reasons at the end. I'm just going to say them now. So this is happening x times. And then if we take a to the x to the y, so we could break this up into two steps. We could say that this is a to the x times a to the x. We're going to put our dot 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 here because we don't know what y is. Times a to the x. And this is happening y times. So then we can break this up even more. So this is equal to every a to the x is a times a and then we're going to put in our dot dot dot. So each of these is happening x times. All of these are just definition of exponents. So far, that's the reason for everything. And then this whole thing is happening y times. So here's what we know. We know that this is equal to a happening x times y times. And the reason that we know that is the definition of multiplication. We have x things, so this is x plus another x plus another x plus another x, and that's happening y times. So a short way of writing x plus x plus x plus x y times is just x times y. That's where the x times y came from. Imagine that there were 3 of these, and then we had 3 plus another 3 plus another 3. A short way of doing that is 3 times 3. If there were 4 of these, then there would be 4 plus another 4 plus another 4. So we would have 4 3 times, or 4 times 3. So that's what's happening here. Okay, this is just the definition of multiplication. And now we did the left side, so we can then do the right side. I'm going to put the right side up here, just so that we don't have to go on to another page. So we have a times a, and this is once again definition of exponents. And we already know that this is x times y times. So now we have the left side equal to the right side. So we could put in our therefore statement. So therefore, a to the x to the y is a to the x y. And we just write in our q ed. So let's just go back through this one more time and do all of our reasons. Okay. So this first one is definition of exponents. A to the x is just a times a times a x times. Okay, definition of exponents. This one is also definition of exponents. We're rewriting a to the x y times because it's being raised to the power of 1. Okay. This one is just definition of multiplication. Well, this one is not really a reason. All we did is we just expanded. Okay. We expanded the first and the second. This one is definition of multiplication. All we did here is just a substitution. So instead of writing a to the x, we wrote a times a times a. We essentially, instead of writing this, we put it in as this. Okay, so we did a substitution. And then our last thing was because of the transitive property. They're both equal to the same thing, therefore they're equal. That was the right side. The left side, this was because of definition of exponents. So this whole section here this was your left side. And this small section here was your right side. So our right side is equal to our left side. Okay. Same thing. Right side equals left side. Therefore, they're equal. Transitive property. You can prove all of these other rules in a very similar way. So you can prove, let's go back. It's not. You can prove rules 2 and 4 in the same way. Okay, I want to prove 5 and 6. I want to prove that anything raised to the 0 power is equal to 1. So we're going to prove a to the 0 is equal to 1. I should change colors. Okay, so this is not necessarily quite as intuitive. So what we're going to do is we're actually going to use this property here, this first property. We're going to use this property, that a to the x times a to the y equals a to the x plus y. So if we say a to the x times a to the 0 is equal to a to the x plus 0, then this is equal to a to the x. So now we're going to take out this middle piece just to see it a little bit more clearly. So we're not changing anything. This is the reason. Okay, we're using this rule. And we're just saying a to the y is equal to 0. We're saying let y equal 0. The reason why we're saying let y equal 0 is because this is what we're trying to prove. We're trying to prove that a to the 0 is equal to 1. So we're just going to plug in a to the 0 and see what happens. And we can do that. We can always just, as long as we're not breaking any rules, we can do whatever we want. And if it works, it works. So we're replacing y with 0 and we're seeing, okay, so what happens? So a to the x times a to the 0, we can add the exponents. So a to the x times a to the 0 is equal to a to the x. And that actually means that a to the 0 has to equal 1. We can put a therefore here. So we're already done. And the reason that we're done is that anything times 1 is equal to itself. This is the identity property of addition. So we're done. So we can write a QED. But the reason that we're going to put in is the identity property of addition. Anything times 1 is equal to itself. Sorry, identity property of multiplication. And we're going to use the same concept to prove the last one. a to the negative x is equal to 1 over a to the x. Okay, same concept. We're going to use this initial property that we see here, a to the x times a to the y equals a to the x plus y. And this time we're trying to show something about a to the negative x. So instead of saying y equals 0, we're going to say y equals negative x. And we can do whatever we want, as long as we're not breaking any rules, and we're not breaking any rules here. So a to the x times a to the negative x is equal to the a to the 0, and we already showed that a to the 0 equals 1, so we can use that. So let's take out this middleman, okay, and just write this. This is an x, by the way. So a to the x times a to the negative x is equal to 1. And we can actually say now a to the negative x is equal to 1 over a to the x. We're ready to say that. And we used identity property of multiplication up here. We are going to use the inverse property of multiplication down here. And what the inverse property says is anytime that you multiply something by its reciprocal, it's equal to 1. So this is the inverse property of multiplication. So anything times its reciprocal is equal to 1. So for example, 3 times 1/3 equals 1. 6 times 1/6 equals 1. That's what the inverse property of multiplication says. Okay. So now we proved all of these rules, which is really nice, but let's put them to use. Let's actually figure out how they're helpful. So one of the things that we do is we use them to simplify exponential expressions. So we take something that looks really complicated, and then we make it much simpler. So there are 3 things that we have here, okay? 3 things that we have to worry about. The first one, we don't want any parentheses. So I'm giving you what you need to look for, and then afterwards, we're going to actually try some so you'll see it. So no parentheses. The second one is that you can only have one of each base. Okay. So we should clarify that. If we have a to the x, the a is called the base, and the x is the exponent. So you probably already knew that, but I just want to clarify for saying one of each base. Sometimes these lines just appear out of nowhere. Okay, and then the last thing when we simplify exponents is that we don't want any negative exponents. So for example, if we wind up with a to the negative x in our answer, we want to make sure that we have 1 over a to the x. Okay, so let's just do a bunch of examples and we'll see how it works. Okay, we're going to start off relatively simple. I'm going to start off on the next page, but feel free to you want to keep referring back to this page here for those 3 rules. So suppose that we have a to the negative 2, b squared, and let's raise this to the 5th power. So if we do this, we know that we're multiplying inside of here. And when we multiply, we're allowed to distribute our exponent. So that's what we're going to do. We're going to distribute this exponent. So this becomes a to the negative 10, b to the positive 10. Okay, so we distributed the exponent. And because we have an exponent raised to an exponent when we're distributing the exponent by multiplying. So if we go back to here, we did our first thing. We got rid of parentheses, and that's how we get rid of parentheses. We distribute our exponents. And you can do this in this one you can't really do in a lot of different orders. You can do it in 2 different orders, but I recommend that you do it this way so that you never forget how to go through this, and you're very, very particular about getting rid of each of the things that you need to get rid of, that you go through in that order. It's the most efficient. So in this problem, we could get rid of negative exponents first. So you see here, no negative exponents and no parentheses. We could have gotten rid of the negative exponents first. But in other cases, sometimes when you get rid of negative exponents first, you have to then get rid of them again, and you'll see that later. So first we got rid of the parentheses. Now if you notice, we're not done. So we have 1 of each base, meaning we only see 1a and 1b. So that's not a problem. We don't have to worry about that right now. But what we do have to worry about is the fact that we have an a to the negative 10. So I'm going to do this in 2 steps, but in the future, you're only going to see me do this in 1 step. So a to the negative 10 can be rewritten as 1 over a to the 10th. So this is 1 over a to the 10th times b to the 10th. And what you're going to see here is that when you multiply, all you did is you moved your a to the 10th to the denominator. We don't have to rewrite it every time. We can just say, okay, a to the 10th, this is a negative exponent, so to make it positive, we just move it into the denominator. So our next step here, so usually we're going to skip this step. We're not going to do this every time. But what we did here is we got rid of negative exponents. So you don't have to write these separate fractions. You can't just move it, okay? You can see here, this is like b to the 10th over 1. So 1 times b to the 10th is b to the 10th. A to the 10th times 1 is a to the 10th. Okay, you should also note 1 over a to the negative x is equal to a to the positive x. Okay, in other words, if you have 1 over a to the negative 5th, you can move that into a numerator. So if it's in the denominator and it's negative, move it to a numerator. Okay, the reason for this is 1 over a to the x, right? But we don't like fractions within fractions. So we can get rid of that. And the way that we get rid of it is we multiply by the reciprocal. Because if we multiply the denominator by the reciprocal, the a to the x cancels. But what we do to the bottom, we have to do to the top. So we have to multiply the top by the reciprocal also. And 1 times a to the x is just a to the x. Okay. Okay, let's take another one. I'm going to number these. Let's say that we have a squared times b to the negative 1 to the negative 1 over a to the negative 4th b. Okay, so this one is a little bit different. So a squared, so our goal is going to be the same. I'm sorry, I should have put this in black, but it doesn't matter so much. Our goal is going to be the same. We want to get rid of exponents first. So we see a negative 1 out here. The way that we get rid of the exponent is we distribute it. Okay, so we wind up with a to the negative 2, b to the positive 1. You don't have to write the 1. I'm writing the 1 here just so that you see that it's there. And now this is a to the negative 4, also b to the 1. Okay, so our first step here was the same. Get rid of parentheses. By distributing. Okay, that means you're multiplying exponents. Now if you see here, there's more than one of each base, right? There's an a in the numerator and an a in the denominator. So we're going to use that rule where if we have the same base and we're dividing, whoops, sorry about that. If we have the same base and we're dividing, here, we subtract the exponents. So that's what we're going to do. So negative 2 minus negative 4 is negative 2 plus 4, or a to the first. And then we get b to the 0. So our b's are actually just canceling out here. Okay, sorry, I'm going to put that in blue so that you see that it's the same problem. And what we did here is we just combined vertically. By subtracting exponents. And there are no negative exponents, so we're done here. Okay. Let's take another one similar to this. I encourage you, by the way, once you feel like you're starting to get the idea, when I write down the problem, pause it, Like I can't, this is not in class, so I'm not giving you time to do it by yourself. So the way to practice by yourself is pause it, do it on your own, and then press play again and see if you can follow along what we did and if you got the right answer. Okay, so instead of mine just giving you one on the board to try on your own, pause the video, try it on your own, and then see if you got it correct. Okay, so let's take the next example. So in this one, we have a to the 5th, b to the negative 4th, c squared, divided by a to the negative 4, b to the 8th, c to the 1st. You could see that these get a little bit more complicated as we go. And this is being raised to the negative 3rd power. So we're going to do the same thing here. We want to get rid of exponents first. So this is an exponent raised to an exponent, so we can just multiply. Okay, and notice everything here is being raised to the negative 3, whereas up here, only the top was being raised to the negative 1. So we have a to the negative 15, b to the positive 12, we're multiplying. Do not add and do not raise to an exponent. So don't do 2 to the negative 3. You're doing 2 times negative 3. Then we have a to the positive 12. It's positive because we have a negative 4 times a negative 3. B to the negative 24. And C to the negative 3. Okay, so we got rid of the parentheses by distributing the exponent. I'm going to stop writing a lot of this. So notice this is always our first step. So our second step is going to be to combine vertically. We only see one of each base in the numerator and one of each base in the denominator. This is going to change eventually. Okay, so, but we see an a in both the numerator and the denominator, which means that we have to combine vertically. When we combine vertically, we subtract the exponents. So negative 15 minus 12 is negative 27. 12 minus negative 24 is positive 36. And negative 6 minus negative 3 is negative 3. So here we combined vertically, which means subtract exponents. And then the final thing that we're going to do is get rid of these negative exponents here. And the way that we do that is we just move them to the denominator. So we have b to the 36 is positive. It stays where it is. A to the 27th goes to the bottom. And c to the 3rd also goes to the bottom. So this was our last step. And that would be our final answer. Let's take another one. A, b squared over a cubed, c. We're going to square this. Now this looks like it's going to be so much harder, but please, please, please be aware that it's not harder. It's just a little bit longer. This is an a over here. Then we have a to the 5th, b to the 3rd. Let's put a c in here. C to the negative 2 over a to the negative 6, b, c to the 5th, and we'll square this. Okay, it looks really long. This is not hard, okay? We're gonna go through it in the same way that we did before. We're gonna distribute the exponents. So this 2 gets distributed to everything in this set of parentheses. It only applies to this set of parentheses, and it's the whole set. So we wind up with a squared, b to the 4th. Be careful here, one mistake will follow you through. Then we have a to the 6th, b squared. Notice we're multiplying exponents. Now here, because we're getting rid of this and it's all multiplying, we can actually just do this all in one nice long thing. So I'm going to put a times here, but eventually what you're going to see is that a line is just going to go through it because it's one fraction. So then we have a to the 10th, b to the 6th, c to the negative 4th, over a to the negative 12th, b squared, c to the 10th. And because we're multiplying, we can just extend this line. Okay, now this is the difference here. In each of the other cases, our next step was to combine vertically. But here we see more than one base. In the numerator, we see 2 a's and 2 b's. So our next step is to combine horizontally. Okay, and again, I encourage you to do it in this order because if you combine vertically, how are you going to know which a's to subtract? Okay, right now they're above each other, but sometimes they're not, and you're going to ask yourself, well, do I combine the a squared and the a to the negative 12th? So you want to combine horizontally first. And when we combine horizontally, we add the exponents. So a squared and a to the 10th gives us a to the 12th. B to the 4th, b to the 6th gives us b to the 10th. And then we have c to the negative 4. And then 6 and negative 12 is negative 6. And b squared and b squared is b to the 4th. So we combined horizontally. So this was the step that we were missing, and now we're doing it. This is the greatest number of steps that we'll ever have to do. It's a 4-step process. So now we're going to combine vertically. Okay, so 12 minus negative 6. Another reason for combining vertically first is that you only have to subtract exponents once, which makes it so much nicer because subtracting positive and negative numbers is more of a pain. So let's try and fit this here. So 12 minus negative 6 is 18. So we have a to the 18th. 10 minus 4 is 6. And then negative 4 minus 10 is negative 14. And our last step is to get rid of those negative exponents. So the only negative exponent here is the 14. So the c to the negative 14 is going to go on bottom. So our final answer is a to the 18, b to the 6, over c to the 14. So we combine horizontally, then we combine vertically. This is our subtracting. And then we get rid of negative exponents. Okay, let's take 1 or 2 more. let's do one that's a little bit different. Let's put an actual number in here. Let's say that we have 2, a to the 5th, b to the negative 3, c squared, and this will get raised to the negative 2 power. Okay, and then let's do over a cubed, b, c to the 10th, and let's multiply this by a squared b to the 4th over a c to the negative 3. This is as hard as it will get. It will not get any harder than this, okay? So we're going to do the same thing. We're going to get rid of our parentheses. So the parentheses over here, notice there are no exponents. It's just a way to differentiate between this fraction and this fraction, because in this fraction, the top is being multiplied by negative 2. We actually didn't need the parentheses, okay? It's just put in there just for clarity, okay? So these parentheses can just get taken out. This one, we have to distribute the negative 2. So we have the 2 here, so be careful. So we're going to just keep it as 2 to the negative 2 right now. I'm actually going to make this a 3. I'll erase that and rewrite it. Okay, so 2 to the negative 3. Then we can just multiply exponents as usual. So we have a to the negative 15, b to the positive 9, c to the negative 6th, over a cubed, b, c to the 10th. This one can just get rewritten. We're just going to take out the exponents. It can just be rewritten as it is. It's not being raised to anything. There are no powers here on the outside. And again, we just extend the line. Okay, so what do we do with this 2 to the 3rd? This 2 to the negative 3, we're just going to move to the bottom and make it a positive power. Okay, and that's going to help here. So I'm just going to rewrite this because it does not look clear. Okay, that's a little better. So we're going to move the 2 to the negative 3 to the bottom, and that'll make it positive. And we're going to do two things at once. We're going to move the 2 to the negative 3 to the bottom, and we're going to combine horizontally. So negative 15 and 2 is negative 13. 9 and 4 is positive 13. And there's only one c. Then we have this 2 to the 3rd. A to the 3rd and a to the 1st gives us a to the 4th. Then we have b. And 10 and negative 3 is 7. Now we're going to combine vertically. Okay, so 2 to the 3rd is 8. So notice we did not multiply 2 and 3. Okay, this is 2 being raised to a 3rd power. 2 is not an exponent. When we multiply the 5 and the negative 3, that's because 5 is an exponent. 2 is not. So we raise it to the 3rd. So this becomes 1 over 8. That comes from the 2 to the 3rd. Negative 13 minus 4 is negative 17. 13 minus 1 is 12. And negative 6 minus 7 is negative 13. And now our last step is to get rid of the negative exponents. The a to the 17th can move to the bottom with the 8, and so can the c to the negative 13th. So we have b to the 12th. Then we have 8, a to the 17, c to the 13. Okay, so let's put in some notes here. So this part was just distributing. Okay. This came from 2 to the negative 3 is equal to 1 over 2 cubed. Okay. We also combined horizontally. This 1 to the 8th came from the 1 over 2 cubed. Okay, we just pulled it out to the side. And we also combined vertically. And then here we got rid of negative exponents. Okay. I'm going to do one last one, and I encourage you to pause the video, do it on your own, and then walk through it with me together. So our last one, I'm going to do it similar to this. Let's do 4 a cubed b to the negative 1 c squared. We'll raise this to the second over a to the 5th b. This is the hardest that it will ever get. Over 2 a to the 5th b cubed c to the negative 5. We'll raise this to the negative 2 over b cubed c squared. And we'll add in another one here. So again, this is the hardest that it's ever going to get. A to the negative 2, b to the 4th, c squared over a. We'll add in a d here. B cubed c to the negative 2 d cubed, and we'll raise this to the negative 2 power. Okay? Absolute hardest. But it's still only a 4-step process. We're going to distribute our exponents, then we're going to combine horizontally, combine vertically, and get rid of negative exponents. So it's the same thing. Distribute, then it's going to consist of adding exponents as we combine horizontally, subtracting exponents as we combine vertically, and then getting rid of negative exponents. It's just a little bit longer to do. So we're going to distribute this 2. That gives us a 4 squared. Don't multiply. These get multiplied. A to the 6th, b to the negative 2, c to the 4th. If you haven't paused this to try it on your own, please try it on your own. Pause it. A to the 5th b times 2 to the negative 2. You'll take care of that later. A to the negative 10, b to the negative 6, b to the negative 6, c to the positive 10. The bottom, nothing is happening to. That negative 2 on top only applies to the top. Okay? And now the last one. We distribute the exponent to everything. So it becomes a to the 4th, b to the negative 8, c to the negative 4, d to the negative 2, over a to the negative 2, b to the negative 6, c to the positive 4, and d to the negative 6. Okay, now we're going to do 2 things simultaneously. We're going to add across, we're going to combine horizontally, and we're going to move this 2 to the negative 2 down to the bottom. Okay, We'll leave the 4 squared for now. So I see an a to the 6th, an a to the negative 10, and an a to the 4th. 6 minus 10 is negative 4, minus another 4 is 8, is negative 8. So we have a to the negative 8. Did I do that right? 6 minus 10 is negative 4 plus 4. Sorry, a to the 0. I make mistakes too. Just take it slow. 6 minus 10 is negative 4 plus 4 is 0. So this is a to the 0. Okay, then we have our b. So negative 2 and negative 6 is negative 8, plus negative 8 is negative 16. Then we have our c. 4 and 10 is 14, minus 4 is 10. And then we have our d, and we only have one d over here, so it's just d to the negative 2. Now on bottom, don't forget the 2. So this is now 2 to the positive 2. We moved it to the bottom. We have an a to the 5th and an a to the negative 2. That gives us an a to the 3rd. Then we have a b to the 1st, a b to the 3rd, and a b to the negative 6. So 1 and 3 is 4, minus 6 is negative 2. Then we have a c squared and a c to the 4th. C squared and c to the 4th is c to the 6th. And then we have a d to the negative 6. Now we can combine vertically. So 4 squared is 16. We'll just write this as 16 over 4. So we could just put that off to the side for now. 0 minus 3 is a to the negative 3. Negative 16 minus negative 2 is negative 14. That's for the b. 10 minus 6 is 4. That's for the c. And negative 2 minus negative 6 is positive 4. Now we can get rid of negative exponents, and we're just going to simplify this. This is a 4. And it goes into the numerator. So the positive exponents here are c to the 4th and d to the 4th, so that remains on top. And the negative ones are a and b, so it becomes a to the positive 3, b to the positive 14. So let's just review what happened here. We distributed the exponents. The 2 to the negative 2 became 1 over 2 squared. Okay. So we combined horizontally here. Okay, we did that by adding the exponents. Then here we combined vertically. The 16 came from 4 squared, and the 4 came from 2 squared. Then we got rid of negative exponents. And that's it. These are all of the properties of exponents and how we simplify exponential expressions. For the next lecture, we're going to talk about radical expressions, which I've said to you multiple times is the same thing as an exponential expression. It works in the same way. Okay, that's it for now, and hopefully I'll post the next video very soon.